I Okay, all can see, right?
Yep.
Awesome. So today I'm just going to talk about physics-informed neural networks, which is so my field is physics, and although I'm in neuroimaging, I'll give a background. So what I do is I try to take physical laws and then kind of incorporate into neuroimaging data to see if I can extract certain patterns. So likewise, in machine learning and deep learning architectures, we have this concept where you can have the normal training, but then you can also have a training based on, for example, oh, I have this law which I know should satisfy the data, and I'm going to use that, the neural network. So this is the thing that I'm going to talk to you all about, how this is applied in a neuroimaging context, in a machine learning context. So most in like day-to-day life, what we have is like motion. So motion and everything. For example, the wave equations, for Schrodinger equations, heat transfer equations. So I might be talking in a bit of physics terms. So if you guys don't understand, let me know. I'll explain. So what happens is that all of these systems that we study in nature, most of the physical systems follow a set of things called partial differential equations, or basically differential equations. What it does is you know how a system should change its state based on a current state. So the rate of change is analyzed by the partial differential equations. So in nature, what you have is we have laws that we already derived describing these changes in nature, and we call them partial differential equations, and we want to see how these partial differential equations can be added into a neural network sense. So when we talk about physics-informed neural networks, it is kind of a subcategory of a thing called physics-informed machine learning. So the difference between, if I just take, I kind of disagree with this a little bit because I feel like physics-informed machine learning should go a little bit, intersect with deep learning a little bit. But what I think is that physics-informed machine learning is another full area where you use physics-informed machine learning in the full architecture of machine learning to see which of the part of the architecture can we adjust to get the requirement that we need. So in a general context, it is not artificial intelligence, or I mean, not what we call GPT-based, AI-based things, but it's somewhat a different way where we use it to basically in terms of simulations or rather systems engineering, something like that. So why do we need physics-informed machine learning? So for example, as I told you, so scientific domains have this engineering scientific problems. They are described by PDEs and ordinary differential equations, which follow these different laws, right? So we want to incorporate these laws. But if we already know these laws, and if we know how to use these laws in a system, why can't we just use them? The problem that we can't just use them is that sometimes if you have a huge system, using these laws to solve them, which will become tedious. And also, you will have to apply to every single point to get a full scale solution to see if it works for us. So this is called kind of like meshing, where you have a grid and you take those grid points and you have to apply it to the equations and get a solution. So this becomes tedious. So we want a way that we can just use a few data points and then kind of have this equation that can solve us when we want it, unlike solve it for a whole thing. But when we so why can't we use just neural networks to train a system where we have the input as the one we want for a system and output as the solution for partial differential equations? So why can't we do this just as a neural network itself? The problem is that when we do that, suppose I'm training a neural network which takes the water flow, and I want to calculate based on what I observe the jet of water coming out of a tap. The problem is for me to train based on whatever is happening here, I will recover a lot of data, and also it will be constrained to what I trained on. But once we know the limitations, for example, suppose I know physical law, which says, okay, this is the fluid and the fluid is incompressible, so it can't expand or contract, or the mass of the fluid is constant. I can incorporate this into the neural network that we're developing. And what it will do is that when it's solving, it will kind of like try to make sure that it kind of aligns with the laws that we adjust. So PINS is not a replacement of the neural networks. It's kind of like a hybrid approach, which helps us to like align what we train in the neural network to a physical law that we already know that the data should satisfy. So the advantage in that sense with that, suppose we know we have a lot of data, we can just deal with having no physics at all. But if we have only a little data or maybe like partial data, we can counter it by saying, okay, this data can follow physics. So whatever the data that comes in later, suppose I'll explain you later on what happens there. We'll say, okay, instead of using data, we are using physics to help us fill that lack of data that we are going to have later on. So in this case, what we have is one advantage that you get in this is that you have this white box, black box approach, right? So neural network is totally black box, but the advantage when you train a physics-informed machine learning is at the end, you use a PDE or partial differential equation. You kind of know the parameters that you are solving here, and it will sometimes, depending on the context that you're using, it will sometimes tell you what this equation that you're getting. So when you get an equation like this, it's kind of giving us an idea of how the data, suppose we do not know how the data behaves, we can use this technique to obtain an equation to say how the data behaves. So this will give us an understanding on how we can use this to understand the data in a sense. So more of a white box approach. So this is just a basic summary of the comparisons of the techniques. But what we do is mesh-free, all the things that I just explained. So I think I don't have to go through it again. But so if I start on the pins, what happens is that in a normal machine learning context, you have this definitions of different, when you are developing a machine learning architecture, you have these different flows of different stages. You have the problem definition, the data curation, the architectural design, loss function, and optimization. So each of these steps can be modified in a machine learning, in a physics-informed machine learning architecture. The difference is that for pins, we kind of modify the last two, basically the loss function and the optimization strategy. So when you talk about the architectural design changes, that is mostly changing the architecture. For example, that's what probably Uday is going to teach us next week on how you change the architecture itself to conform with new physical systems. But what I'm going to talk about is the modification of the loss function in a normal neural network to align with the physical system. So when you consider physical system, there are three things. First is called observational bias. Observational bias is how the data will generally behave. For example, now when we use image data in training a CNN, we know that translations, rotations, and all these things are invariant, which means if you have a face, if you have a cat, if you change the shape, or if you just rotate the cat, it's the same cat. If you just flip the cat, it's the same cat. So this is called kind of a symmetry in terms of rotation, or called the invariance in terms of rotation, like translation or resizing. So those things are the observational bias that we can incorporate when we are doing this pins. The inductive bias is known as, suppose you know that it is supposed to follow it is supposed to follow the conservation of mass. So mostly inductive laws are laws that we already know, that we know, okay, it's supposed to follow the conservation of mass, conservation of energy, And then we use that to be added into the machine learning. Most of the time, this part is the one that adjusts the architecture in that case. And the last one is learning biases, is how we learn. Pins mostly adjust this learning bias, saying that, okay, we are going to use the partial differential equations at the last stage, where we say, when you are learning the dynamics of the system, use the pins to adjust the things. So if I just go start with a general explanation of this before I go in deep into pins, what happens is, this is just a normal architecture which people have developed to using physics-informed machine learning in fluid mechanics. So one thing that they do is, so if you look at the end, the third step, the physics-informed architecture, what they do is they kind of change the full neural network architecture to conform to a specific, for example, a bias that I told you, or the second bias which I told you about. But what I'm talking about is, I'm talking how I can change the physics-informed loss to have the change in, to have the training so that it conforms to what we want. So if I go to the physics historical context of the pins, so usually pins were very, like, we think that pins are very new, but it's not. It is actually older than deep learning networks. The only issue that it had was it did not have, so when you are doing the solving pins, it kind of does the training and also kind of like solves the partial differential equations. But the problem is that when you are solving the partial differential equations and training, the amount of GPU power or the amount of calculations it requires is too much. So currently it's becoming a very prominent field because now we have a lot of computational advantage right now, although this is a very old field. So I'm going to dive into a small explanation of how we can apply pins to a small scale scenario to teach you like how to get it a better sense. Okay, so suppose we have a pendulum, okay, and we have a data points of the pendulum where the pendulum oscillates like this. And when it's oscillating like this, we can do is we can get the outputs of the, we can just take an image of this and we can train the neural network to predict the next point. Or rather, we can use the neural network to predict what the, when the time goes, where the theta t value is. But what's going to happen here is that, suppose we have, or in this case, we have 5 data points. Oops. Okay, if you have 5 data points in this case, what's going to happen is that when the neural network trains, it's going to only adjust its data up to the 5 data points it has, because it has no knowledge of the rest of the data. So what we can do is, for a simple pendulum in physics, we do know what the solution is. Rather, we do know the differential equation that satisfies this motion. So what we are going to do is, we are going to say, okay, at the end, you have the time t, and you have the prediction that you get from the neural network. What we are going to do is, we are going to get this prediction, and we are going to use the knowledge that we know, where the differential equation says that, okay, the angle over here differentiated would equal something. So that we are going to use it in the next part to kind of add it as another loss function. So what we are going to do is here, what we are going to do is we have this part, and then we add another rather another layer, which kind of says, okay, you take this output, put it into this equation and get the differentiation, and you take that and see if it is satisfying the equation that you want. So now in this case, the advantage is that, suppose we only have the data for this point. What happens is that when you add this equation, we can use any of these points as sample times to just randomly add to the neural network, get an output. Whatever the output the neural network gives, we can differentiate it, get the loss function through the physics informed part, or rather get the loss function through the differentiated part, and then check if the loss function is high or low. Using that, we can train. So even though if you don't have enough data, what we can do is we can kind of add pseudo data, which to see if it satisfies, and then train it step by step. So in a sense, this is
just
I
a
will
question.
go.
Just a second.
Yeah,
Can you go back? Like the previous slide.
yeah,
So in this, you have mentioned the equation of the pendulum, right?
yeah,
But in real world, we actually don't know the equations, right? So whatever data sets we'll receive,
yeah.
however limited that may be, but the equation will not be known, right? So how will we pass the initial equation to compute the loss on? So how will that work?
Oh yeah, I'll get to that. So in this context, what I'm starting from is a system where they know already initial equation.
Okay.
So there is a way there. So the next stage of pins would be that. Sorry. The next stage of pins would be that essentially where you do not know the starting of the equation, but I'll get to that after this. So yeah,
Okay.
Okay, so this is for systems for which you know that they behave in a certain way. The
exactly.
dynamics of the system, you know them beforehand, and that's what you're injecting into the neural network.
Exactly. So right now, I assume that I know the dynamics of the system. I just want to train a specific case of it. So for example, suppose I know fluid mechanics, okay? I know how waves should behave, but I do not know how the waves should behave in a specific container. Like for example, I have this pool. I want to see how the water behaves in this pool, but I know how generally water behaves. So what I do is I get the equation of general water behavior, and I get the machine learning part of like a video of the pool. And then I just say, okay, this is the laws that it should follow. And this is the data I'm giving you. So kind of train this to follow this law. So it's kind of solving a partial differential equation for a specific case, if that makes sense. So, sorry. Okay. So in this case, just to give a recap before I go into a detail, I'll explain you into a detail more. What it does is these things, as you can see, if you have a general idea of a spring, if you know the time, the extra points that we take in terms of time to represent the pseudo time points, you call it kind of like a colloquial, shoot, I forgot the name. Okay, very well. I'll get to that anyways. So the key idea is that you can apply two kinds of equations for this at the end. If you know the partial differential equations, knowing the dynamics of the system, you can also add the boundary conditions of the system as a boundary loss as well. So kind of saying, okay, these are the system boundaries, whatever points that goes through it, just ignore that, something like that. So if I go into detail for the system, this is what happens. So ordinary partial differentiations are normal things where you have like a single differentiation with respect to y, right? So partial differential equations are ones which have like 2 or 3 variables which differentiate with respect to each other. So in this case, this is kind of like a wave equation type of thing. For fluid flow, this is like a very common equation for like heat transfer, fluid flow, and light and everything. So what we are going to do is the first step is using pins to solve a PDE of what I mentioned before. What you do is, in this case, suppose this is the PDE that we consider. This is kind of like the differentiation of, let's say, fluid flow. The velocity of the flow with respect to time is equal to some parameter times the velocity of the flow double, the second differentiation of the velocity of with respect to space. So now I need to define a thing called the physics residual loss, which we are going to use in the pin. That is basically using, okay, just the same equation, just take it to the side and just say whatever the quantities that we get, differentiate it, subtract, and take it as a loss. So this part is just saying that this is the equation that we are supposed to satisfy. When we get some output, we treat this as the loss function for the physics part. So how do we integrate it to the loss function? So the way we integrate it to the loss function is, for example, in the normal neural network, we have the data loss, which is the general loss functions that we use in day-to-day things. So when you have this data loss, what we are going to do is, if you can remember, the way that the neural network was developed was, you have the neural network, you give the input. Suppose in this case, the input was t, time, and x, and what we want to get is u. The neural network will take time and x, will generate u, and this u I'm going to take to train to again calculate to see if it will satisfy the for example, this condition, the physics loss, the physics residual loss. So what we are going to do is we use the neural network to get a u, and then you differentiate it within the network itself in the next layer, and then it generates another loss. So in this case, you're calculating two losses, and the total loss will be minimized to get the specific differential equation, like the specific solution for this given scenario. You get that point? Like how the loss function is integrated, like integrated with the physics thing. If you all have any questions here, I can just answer before I go to the next part. Okay. So what happens here is the advantage that we have, the reason that we can use differentiation right now is that because we have like this thing called this is the same thing that I explained before. You just use optimization like normal optimization that we currently use, like Adam or some specific scenario, which kind of converges. And the advantage that we have right now is we have this thing called automated differentiation, which kind of use faster differentiation so that we have much more high precision using and avoiding errors, which helps us to apply pins right now. So what automatic differentiation does is something like you have a function like this, and it kind of takes the chain rule and kind of does higher order derivatives for each and every one without like, so example, if you have finite differencing, it will be unstable, and also you can't do faster calculations. So the advantage of pins is this is a very crucial element in the pins called automatic differentiation, specifically in PDEs. You use this to calculate faster differentiation across the equation to get the output. So to get a recap on what I told about how these pins work, if it was not clear, suppose my input was time and I wanted to predict the angle which the pendulum moves at a given the next time point. I first train this neural network to output this theta prediction, and then I use this theta prediction and I use this to differentiate between the loss I know, and this loss I know will give me a specific loss depending on the condition I use. For example, if it's boundary condition or if it's the differential equation which governs the dynamics. So what I'm going to do is I take the output of the neural network, I put another layer which has this, use my equation to see what if it's satisfied or not, and then I use that as my entire loss function to optimize the neural network. So hopefully this is all good, and I can just go through it. Yeah.
Yeah, that's all good.
Okay, then I can just go through another example just to get you all clear on that. So this is
I had one question. So for example, if you put any data, if you are putting time through a neural network, you have input as a time and you're getting some output. So the output that you get will be one numerical value. What do you mean when you say you are going to differentiate it with respect to time and something and get something out of that?
Okay, that's a good question. So okay, if in this case, can you see this wave equation? Do you know about wave equation by any chance?
No,
Okay. Okay, sure. So for people, okay, so let's go something simple. What we are doing is, suppose I know something called, I have a relationship between y and x, okay? And I have a differentiation equation saying dy over dx equals something. Okay, but I need to solve for y and x. But the one I know is how it changes. We don't know what it is. For example, if I say if I have this pen and I I want to see how much heat is at this point and this point and this point. I need to know how heat transfers based on these points, right? So suppose if suppose this is a rod and I'm burning this end using something, and I want to see how much heat is at this point. I know an equation which governs how much heat transfer occurs over here, but that's a differential equation. It's saying that, okay, when I differentiate the transfer, or rather the speed of transfer of this is 2 meters per second, something like that. It goes this fast, but I don't know the speed here. To know the speed, we do kind of a thing called integration, something like, okay, this is how much the speed is, this is how much time took, or rather this is how much distance it travels. So the value over here is this is the heat. You get that part? So it's like kind of integrate. So solving a PDE means you have a equation which says how fast it moves. You integrate to see, okay, this is at this point, this is the value it has. At this point, this is the value it has. Do you get that part?
Yes.
So now, so think I have this equation and I'm using a neural network to get this data. And now I'm training the neural network to predict this. I have no equations at all. Okay, this is not a general neural network. I'm just using like 3 data points to predict the next one. I can still do it because neural networks are good approximators for functions. They can do it. But the problem is they do not know the laws that we follow. And suppose if it has like 3 points, which is closer to here, what it's going to happen is it's going to kind of like overfit so that it only knows to predict this area. But suppose if we can have a way to give the information to go to this range, what it's going to use is, that's what with pins what we do is we give the information, okay, you don't need to know this data, but we can tell you what pattern this data should follow. So at the end, so what you're doing is you're doing that. You're giving the pattern for it to, like, kind of giving a equation for it to follow. It kind of constrains the outputs that it can give, right? So your question. So what it does is, suppose in your question, but so I have this starting point and the neural network is predicting the outputs at these points, right? So what I'm doing, I'm taking the output at this point and redifferentiating to see the speed of this point. It's like, for example, the physics law I know is that I know by law, this is the speed this point should follow. And what I'm going to do is I'm going to take the value I got through the neural network, differentiate it to see if the speed I get is equal to the law that I should get. So now I take the speed I got versus the law I have. I take the subtraction of it, and that is the thing that I take as the loss. So the good thing is that,
can you go to your previous slide?
yeah.
So for example, in this network, you have input as t and you're getting theta pred.
Yeah, exactly.
Yes. So the theta would be just one number, right?
Yes, one number. So it doesn't have to be one number. It can have many variables, but in this case,
so yeah, in this case, let's say that it's just one number that you're predicting for one training point.
exactly.
And that number that you get, what so you are going to put this that number into these equations.
Yes.
And for example, in the differential equation part, you have a partial derivative with respect to time of theta pred. So if you just have one numerical value, what does differentiation on just that one value mean?
Okay,
Is my point. Like, how do you calculate this? Is my question.
So if you pay attention, it's differentiation with respect to time, right?
Yeah.
So what happens here is that when you give a time point, you have a prediction, right? So suppose you have like for example, it's like saying, okay, I think I know what you're meaning. You're asking how do I differentiate with the
Yeah, how do you put this into equation? Like,
okay, but at this point, the time that is related is this, like for example, for this instance, the prediction is related to this time. Like that like for a unit output,
Yeah.
the input output are related, so you can use that in the differentiation. So this is where this part, I get what you mean. I'm exactly not sure how to answer that, but this is where the automatic differentiation thing comes in. Kind of
Yeah.
like it kind of like plots it. So from what I read, I was not sure exactly how it happens. Maybe once I get understand how, maybe I can like tell you all guys next time. So from what I understand, it is like it kind of uses like you plot it in a graph, like all the outputs, and kind of gets like this like, so for a single, like for example, instantaneous. So you when you draw a graph, like suppose you have this like thing, you can get this with like gradient at an instantaneous point, right? So it's something like that, but I'm exactly not sure, but I get what you mean.
Yeah.
The concept is there, but honestly, it's related to this automatic differentiation thing which they develop, which I'm exactly not sure how it does it internally.
Yeah, that's what I thought also. There's something with automatic differentiation. How do
Yeah,
you do something like this?
maybe.
Could be
Yeah,
like
but if you guys know
they
anything,
pass.
feel free to contribute. I might not. Yeah.
I
I
was
mean,
saying like I have
yeah,
here's one solution that's coming here. Like maybe they pass a lot of batches at different time points, so they have different predictions at each time point, and it's easier to compute the derivative when you have more than one point, right? So that could be one reason. I don't know, but this is just from top of my head.
Yeah. This.
yeah. I mean,
Yeah.
derivative is just difference of two values, two theta values, right?
Yeah,
So
correct.
if you get two theta values for two time points, you take the difference, you have the d theta or dt.
Yeah.
Yeah. In that
So
case,
Could be like that. Could be like that.
the question I think Arath has is, in this case, we are having just single time point. How do we get two time points, right?
yeah, so for each, so if you're using just the first derivative, then you need at least 2 points to compute that derivative,
Yeah.
right?
This is where the automatic differentiation come in, but I honestly,
This is something good to look at, maybe.
yeah, I kind of like brushed it off, saying that it's just a differentiation
Yeah, it's just
thing.
happening. Yeah, we always do that. We always do
Yeah,
that.
yeah,
You just brush it off. Okay, so it's happening. We just put in the loss and it's working. Yes.
yeah. Okay, I'll
Also,
look
like
into this and
second
let you
order
guys know.
derivative is also being computed. Those with the order of points change, right?
Hmm.
So it applies a chain rule at each
Cool.
step, producing the exact derivatives. So that's interesting. Okay.
I had a question.
Yeah.
So from what I can understand, like you are solving the PDE for like a particular set of initial conditions, right?
Uh, yeah, kind of.
Like if I change the initial conditions, say, do I have to retrain the PDE
It
for
depends.
those
For example, in this
initial
case,
conditions?
oh yeah. Oh, sorry. So if I understand your question, it's like asking if you change the initial conditions, right? So
Yeah.
the difference is this is not learning the initial conditions. This is learning the context of the system. For example, like I told, for example,
Yeah.
if you have a pool which kind of circulates and you're using it to, I know the laws of motion of water, and you're using it to predict how the waves go.
Mm-hmm.
If you kind of like shake the water initially in a different way and shake the water again in another way, even though the way how the initial conditions you give at these two instances are different, the way system would behave physically would be the same in both cases, because the boundary conditions like the pool size, the depth of the pool, everything would be the same. So the physics
Okay.
which follows should be the same.
Okay. So like we can just change the boundary, the initial conditions and be able to essentially influence the system.
Exactly, because what we are
Okay.
doing is essentially learning all the parameters that is unique to a specific system in this case.
Mm-hmm. I
Because
see.
we know the laws, we just need to know what is unique to the system with these laws. So that's what we are kind of doing. So it doesn't matter where you start, it should still follow the same things when
Okay.
it will, if it follows the same equations.
Okay. And
according to
like
my understanding.
awesome. And are there like situations, I don't know, but are there like situations where these initial conditions play like a key role? So depending on what the initial condition is, that can have like a different outcome?
Uh, they do kind of play a key role. For example, the let's see, initial if so whatever the condition that you treat. So one of the examples when I was reading was that they say if I'm using the explanation which I gave to Arun before, if you
Yeah,
are consider the heat transfer here, my initial conditions should lie within these points. So it's called the boundary condition, where
yeah,
if I give a point outside my system, so like in this case outside the pen, saying that
yeah,
I start my heat transfer here, the system can't do it because it's outside the constraints of the system.
I
So whatever
see.
the condition that we do should be within this boundary that we
I
put it
see.
on, and the boundary which we gave the loss of it on.
Yeah.
But the
Okay, that
good
makes sense.
yeah, but the good thing of this is that this is extremely tolerant for noise data. So for suppose when you are training it, if you
Mhm.
have noise within this, but you make sure that your system should follow this path, whatever the noise data that you get, it will not generalize to noise, but it'll try to generalize this to the system. So that's
I
the
see.
huge advantage that pins have in terms of like all the others.
That's
Okay,
pretty
so
awesome.
if I'm not wrong, for each for each physical equation that you're training for, you will always have that initial condition in your equations somewhere that you are training for, and this way, when your network gets trained, it's actually learning the dynamics of the system on the basis of the initial conditions, whatever is there for that training point that you are giving.
That's not the initial conditions. Let's call it the dynamics of the system.
Yeah, so the network is learning the dynamics and it's invariant of uh, mm, the initial conditions. Like you can make
You
it
you can give it
invariant.
initial conditions, yes.
You can give it initial conditions, but it's not learning the initial conditions for which you're like
It's learning the dynamics of the
it's
system
learning the
if the
dynamics.
system kind of follows the pattern. Like
Yeah.
for example, in this case, if the system follows a general pattern for this specific system, something like that.
Hmm. Okay.
So
Hey, I have 2 points in the ongoing discussion. First, like as we are seeing here, the first layer is or the input is a time
which one?
parameter.
Sorry.
The
Sorry.
the yeah, this slide itself.
Yeah.
Like on the right, you have automatic differentiation, and let's
Yeah.
call that as a like regular neural network. So the input parameter you have to represented it as a time parameter.
Yeah.
Should like this is what I am thinking. Shouldn't it be a multi-parameter input over here since we are talking about PDEs and there could be a lot of variables governing the equation, for example, time and space across all the dimensions. So if, for example, we have T and X over here,
Okay.
then the data prediction that we would be generating, the all the discussions and fuzz that was being created just few minutes back on how we will calculate, wouldn't it solve the problem if that is how we govern or define the input parameters? For example, if we define input parameters across T and X, the initial set will give us something. Then let's say T1 X1 we have output 1, at T2 X2 we have output 2. We have a more controlled output mapped to a particular parameters that
Okay.
would actually help us to define partial differentials.
Okay. So you're telling like essentially pull out everything and then get the differentiation?
Yep.
Yeah. Yeah.
Not sure
That is
how.
a good point. I don't know exactly how it happens here. That's the issue, but I'll let you guys know for
Yeah.
sure once I read a little bit about it. I hope that was the question, right? Was it?
Yes.
Yeah.
I was just thinking and thought
Yeah.
like
Yeah.
it could provide a way.
Yeah, I would
Yeah.
think that, like, because in this case, the advantage of pins is that you are not limited with the data. You can put imaginary data points within the system boundary. So suppose
Yeah,
you have
but
10
we
data
are
points.
surely limited with parameters, right?
Yeah, we
For
are limited with
example,
parameters, but we are
yeah,
not limited with data. For example, I can put suppose my length is here. I can put like fake data points here and still train the network to follow the laws because it should. Something like
Right.
that. So
Yeah,
yeah, your
the
point could
problem right
happen.
now in understanding is just that when you put something through the network, you get one numerical value, and how do you differentiate that one numerical value to put it into the loss function?
Okay, yeah, that's true. Okay,
That,
that's something that
that's the
I'm
summary.
also no worries. But we could look at another example to see if we
Yeah,
can figure it out,
yeah.
but I'm not sure though. So what happens here is, in this case, as he asked, the previous person asked, so in this case, we have multiple inputs because the wave equation essentially takes x, y, and time. And we are predicting, in this case, the acoustic pressure. So something like, imagine it's like kind of like the velocity of the water flow. Something like that. This is a common wave equation. So what we are doing is, first of all, we are training a neural network which can predict the output of the velocity itself. No physics here. Just saying what this is saying is, just get x, y, t, predict the output of u. This is the ground truth. And now what you're gonna do is, how you're gonna train this is through a simulation, this ground truth simulation for around 0.02 seconds. We are going to train this using from the simulation just to understand the dynamics of the system for like 0.02 seconds. And then we are going to put this physics part using this output, and then we just take this output, do the differentiation here, and you use the physics laws to predict it. Now you use it to predict for up to 0.2 seconds. So almost 10 times as much. So what happens is that, so this is the paper that they showed. If this is the ground truth, a normal neural network, if they do the training up to 0.2, that is okay. Then if they use the inference, this is what they get. What the pin does is, what the pin essentially does is, it kind of follows the laws that we get. And this is the difference between the neural network output, where as you can see, after the training sample, like the pin was trained up to 0.2, and after that, it has no knowledge of how the system should progress, although it does give kind of like a approximation of it, but it's not enough. And the difference between the actual ground truth and the pin itself is very high. But when you take the pin, the ground truth versus the pin where it follows the pattern, it's like the difference is very low. Essentially just showing when you have a multi-variable, that's how you do it. The same concept to just add everything. Although this does not answer your question, Arath, I shall figure it out and let you know. So, but the next what I'm going to answer is the question where suppose we do not know about the dynamics that we are going to solve. Now, in this case, we need to figure out how we are going to, what is this partial differential equation that we are going to, that governs a system. Suppose we have a system we do not know nothing about. I mean, we should know something that it kind of changes. If the system changes its state over time, it is following a sort of a partial differentiation. And suppose if we kind of observe that the system is changing its state in terms of space, then we say the system is partially differentiable in terms of x or y. Suppose if the system changes its state in terms of time, we say the system is partially differentiable in terms of time. So with this knowledge, but we do not know the values or rather the coefficients or the exact equation that the system follows. We just know that it changes with respect to these things, but we do not know exactly by how much or like what the contribution of each is. So what we are going to do in this case is we are going to put variables to each of these parameters that we differentiate and treat it as a trainable system as well. So if you look at it a little bit better, what we are going to do is for the residual loss, wait, if we go up. So in this case, if we have the dynamic, if this is just the output of the system, and this is the differential equation that we do not know, so we kind of put this lambda, just saying that, okay, lambda is also a trainable parameter now, since the differential equation is also unknown. So the residual in this case would be the normal, the neural network approximation, plus whatever the unknown operator should give. In this case, this is how we get the loss function, the same thing, but the only difference is now we just put additional parameters there. One catch of this is when we do not know the partial differential equation and when we want to train the partial differential or rather figure it out, we need more data points. Of course, we need a lot more data points than we had before because we are figuring out more parameters in this case. But the good thing is that we do know how to restrict these parameters in the dimensions that we know. For example, if it's space, time, or something, we do know the restrictions of these dimensions in that sense. So this is kind of like a very common equation that everybody like in physics and everything, everybody knows this. I call it the Burgers equation, but it's supposed to be Burgers or something. So what it just says is that so if this is the function, if this is the function that kind of like represents the state of the system, I know that the function depends on this time derivative, which this is the time derivative, this is the function, this is the special derivative, this is the special derivative, the second special derivative. It's kind of like a very generalized equation. So what it's saying is, since we know that the system should behave in x and t in terms of these derivatives, we just put lambda1 and lambda2 as the coefficients that we are supposed to be training, or rather the system learns, so that in here the system learns the partial differential equation itself. So this is where we kind of use the pins as a system where it trains us to use it kind of gives us the unknown PDE. So where if you have a lot of data and if we can't find a solution by ourselves manually, this is a system we can use to get an equation of judging the system. So kind of like this is more like the white box approach, which kind of shows us what it's doing under the hood, as opposed to what we know before. So in this case, they give initial thing, and okay, that the thing is called collocation points. The collocation points are the things, the kind of like random points which we just take to fit into the thing, just to sample again. So that's you don't. So the advantage of pins is that you don't have to have actual data. You can kind of get this like pseudo data from within the boundary, which you can, because after you train using the data already, you know, it will kind of have this differential equation, and these points should satisfy this differential equation, and hence it kind of trains the networks using that. So this is how you train a thing which you do not know. Basically, you just say, this is what, using the knowledge we know these are the relationships between the variables, but we do not know how much the relationships are different. We just train this how much by using the neural network along with training the neural network as well. Is this clear for you?
Okay, so if we are also training the PDE, the
Yeah.
coefficients of the PDE, so even if you are using some deep network for that, you are saying that if you get that PDE, that means that you have made your model interpretable in some sense,
Yes,
because you know what it's solving.
exactly. So the way that you say you made the model interpretable is that now you say that you know how the heat transfer is related to x, but in this case we are giving you the equation. So when you train this, and if you extract at the end these lambda values, it will give you the differential equation that this system would satisfy. With respect to the variables that we defined earlier. We are saying these are the variables that should have relationships, and they are saying, okay, we kind of found, the network is saying that, okay, we kind of found these ones for these relationships, and these are the ones. So what they found out was that, I didn't put it over here, what they found out was that when they trained it, the partial differential equations that they kind of trained through the network is accurate up to a 2% error if the noise is less than 10%. If the input noise is less than 10% for the data points, the accuracy of the output of the trained like the PD that we obtain with respect to the ground truth PD is around 2%. So it's really good. So
Yeah.
how it works is still a white box, but a black box, but it gives us something that we can still interpret to say, okay, this is the equation that we got that kind of governs it. Based on what we have seen, there might be a variable which we didn't say that it's there, but is actually important. But maybe the neural network is handling that part. We do not know.
Mm-hmm.
So in this case, what we give is what we get out, kind of thing.
Yeah. Okay.
Yeah. So in this case, basically just the same thing, just showing how an actual neural network would work. You have this target functions, and you get the variables, you do the differentiation, and you can use the same loss computations. If you have the loss in terms of like alpha, beta, like A, B, and blah, 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 you can train this stuff to understand what the underlying equation is. And then this is how you just do the basic training, as you guys do in the normal sense. So this is okay. I think I'm going more time. So, but this is just a next step of the PDE, like pins. It's called B pins, and they're saying like since right now you just get the output saying that okay, this is the output for a given thing and this is the trainable thing. The Bayesian pin essentially says that suppose we know that this distribution, like suppose we have a set of data and we say this data should follow this distribution, and we somehow incorporate this knowledge of the distribution into this system by using these two methods that you show. And once you do that, what you can get is at the end, you can say, okay, this is the output of the system within this confidence interval. Like this is how much the output kind of relates to the like so let's say it is 90, like the range or something like that. This is mostly used for neuroimaging or like for like medical systems where you say, okay, the efficacy of something predicted by this is this much with a confidence bounds of 95% or something like that. So this is just saying that how we can incorporate using like two like mechanics we know, the knowledge of the data, the distribution, the data or the output should kind of follow. And using that, we can kind of get a probability or kind of a distribute like a system just saying that okay, this is accurate up to these bounds, something like that. So this is yeah.
Can you give an example of using B pins for some problem?
Okay, so for example, okay, suppose I'm training uh, okay, I'm training to identify if a person has some kind of uh, let's say I'm training to identify a person with ADHD, let's say, and
Okay.
suppose I somehow know that this neuroimaging data that I get, I'm using neuroimaging because this is my comfort area. So suppose I know that the neuroimaging data I got somehow follows kind of some sort of or rather the model that I'm using follows some sort of a known pattern. Okay.
Mhm.
And this known pattern always follows data, or rather the input output for this is kind of like having this its own dimensional space with bounds. So what it does is, if I train my system and it gives the output, it kind of says that okay, within this does this training, like the value I got, is this within, like for example, if I say okay, this person is ADHD, and then it kind of backtracks to see if it confirms with the model, and if the model is confirming with the initial that assumption that I thought or something like that, then it can say within a confidence bounds of this much, or rather accuracy of this model, this is the value you get, something like that. That was a bad example I gave.
Still didn't get it.
Yeah. It's like so something like so for example, how do I say? It's about it's kind of like, for example,
Is it something like you're introducing some prior into
Yeah,
the so
exactly.
so 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 what kind of a prior would you integrate like for your problem in neuroimaging? Let's say you were using whatever EEG or
Okay,
something.
the
What kind of a prior would you use there? Like
okay.
for
So for
let's say if you're just solving for like you have CT images and you have some portion of your that you're segmenting out of it, and you know that correct me if I'm wrong, like if you have some segments that you know that these segments always follow some distinct pattern or something, is that the prior that you inject like in this like
okay, something that I'm not sure if this is the exact thing that's going on here, but something that I would assume that goes on is something like this. So as you told, in the brain, you have these two, suppose I have two locations that has a higher connectivity between those two regions than the other regions of
hmm
the. So now my belief of my parameters, suppose my parameters is to observe how the information moves across the brain. And my prior is that there is more information transfer between these two regions than the other regions, my prior. And then I get the neuroimaging data and then see how, like, for example, the model explains the data. Now you kind of like get this thing, right? Now you get this understanding, okay, is it still following my assumption or not? And so if my initial, like from neuroimaging, I say, okay, this is the thing that you're supposed to get, and this is what the kind of the model gives. How much is it conforming to the standards that we thought before? Something like that.
okay, okay,
Kind of something like that.
okay.
Okay. But if you need more information, I can just go into the deep in depth for the AD and this one and get back to you guys on that.
Yeah, that would be like if you can point us to some resources about learning for learning
Sure.
pins and B pins, some papers or some resources, anything that would be great.
Sure. I think so in this case, this is just saying what pins are solving, the use case of pins, which is not like this. If I give it like it's just saying whatever, if there's noise data, whatever you guys solve, you can just solve it. And then simulations, you can just solve it. Real world data, if you know the mechanics of the real world, it'll make it so, like for training robot arms, you know the mechanics of everything, you just say that, okay, this is what you do, train using that, using not just the video input. Now, in this case, you know the physics of the input, so it trains better and more accurately. So, so this is just saying the advanced thing. I have no clue on this. I just put it just for y'all to research if you guys have time. Uh, uh, there are many versions of this. I have not gone into depth in this one. Sorry about that. The wait, I'm just getting to the resources. So the practical challenges would be, the problem would be again, optimization is very difficult if you're essentially learning the PDE as well, because kind of it adds more parameters rather than the neural network itself. In a way, it kind of restricts the neural network, but it adds a little bit more parameters as well. Right. So, and then you have like imbalance in kind of like residual sums of this and that. And also, one more thing to note: in the literature, a lot of people say that this loss imbalance, for if you have the loss from the neural network and the loss taken to the physics, sometimes they are not working in unison; they go against each other. So this finding balance is, I don't know why they go against each other, because I would expect that the neural network should learn the same thing that the PD should describe. That I do not know, but they say certain times they work not in unison. So finding this thing is also important to see which loss you are supposed to minimize the best. So to get a better performance, because you can kind of like put a just a multiplication to control how much of a contribution of each loss is to the main loss function, to have like a sweet spot for both of them. And yeah, so these are the thing. And at the end I have some resources. Okay, so this is just a very over the top overview, guys, for you guys. So I'll try to get information on the AD and the question that Arath had.
Mhm.
Otherwise, I hope you guys got just a overview of it.
Yeah, I had one query. So I work on time series forecasting, and
Yeah.
I have noticed, like from what I could gather from the presentation, that these networks are very good when it comes to time variant data, right? So
Yeah.
they can actually construct a function that is very well generalized in the future, right?
100%. Yeah.
So, are there any studies, the existing studies comparing the physics-informed neural network with traditional machine learning, deep learning models? Can you
Oh,
like, are you
so
familiar?
comparing them, I'm not sure, but you see the second link over here with the GitHub. So that kind of summarizes the pin papers currently out in all domains. So it has like a huge collection of all the pin papers in all domains. That's a really good one to check. I'll send you guys this one to check. So in terms for your question, yes, it is. If you have understanding of kind of like, for example, in this case, I think there is like if you're doing financial stuff, there are specific models that you have already over there, kind of describing the behavior in a long-term sense. Yes, you can incorporate them to the neural network. But in terms
Yeah,
of
I'll
what they have
take a
done,
look.
I'm not sure still.
Yeah.
But
So for example, let's say we have the EEG data,
yeah,
right? And it's the EEG is different for each person. There's a lot of subject level variability there.
yeah.
So can we use this like physics informed thing there to add something in the time series? Let's not even EEG, if we have a normal time series, can physics informed be used for a time series data which we know follows some kind of a pattern, that we are assuming that it follows some kind of a pattern and some form of constraints, but
Yeah.
we actually don't know what the like what the differential equation for it would be, and
Yeah.
what will be the constraints. We don't know that, but can we model it as something like physics informed stuff? Is it possible?
To be honest, I would think so. Because essentially the problem is the okay. Now depend on what you're training it for. So for example, what are you training it for in terms of, so are you training it for something that is unique to a subject or unique to a group? Unique to a group, for example, if it's generalizable for the whole population. For example, if
Mhm.
you're trying to find out how the brain works for all the population, and then you find a PDE, yes, you can kind of like work on it. I don't know if it will give good results, but it will work. But if you're going to find a subgroup, for example, if you're like just going to take one individual to see how this person's brain would work, that will not work. Get what I mean? Yes, it will,
Mhm.
because if you're training using a larger group of EEG data, what it's gonna do is, if you have a partial differential equation which kind of you're kind of constraining the model, when you constrain the model, what it does is it kind of treats the outliers of these as just like actual outliers and just removes it. So in a
Mhm.
way, it is good in terms of like converging the system, like converging the NN. It helps to converge the NN for a little bit better in a way. But also in other senses, if you are comparing between like pathologies, if it does not have enough data to identify a good pattern between the pathologies, or if you don't have a good prior to say this pathology response like corresponds to this factor in the brain, for example, this kind of change or partial differential equation or something like that. If you don't have that, it will just try to learn the things that are common between them. It will not learn the different, like if you don't know what this is. But if you have a good assumption of what this is, yes, it can. But
Mhm.
that's the issue that I would say, like the balance of that. Yeah.
Okay.
Yeah, this is something that the one you told about the EEG, that's something that I've been working on. I think we discussed
Mhm.
about this.
Yeah.
Yeah. But yes, it has the pros and cons as well.
Okay, that was a great presentation. Thank you so much,
Oh
Dilanjan.
yeah. Sorry, I'm not good in certain areas, but I think I kind of brushed off the AD part. I'm like, it's just differentiation.
Yeah, I know.
Yeah.
So yeah, it happens. So in normal neural networks loss, we have whatever we have in as loss, we also differentiate there. But the differentiation is respect to some activation function, and that gets it back to the original value that we are using. Let's say for sigmoid, we have when we differentiate the sigmoid function, we get something like the original values or something. You have to just put in the whatever you are getting there, and then you differentiate, and then like differentiation is equal to the original values itself.
No, what you're talking about is like the backpropagation, right?
Yeah. So if in backpropagation you're also differentiating and
Yeah.
doing stuff,
But
right?
this is different from this is different
Yeah,
from
this is just calculating the loss function. You need
exactly.
derivatives, different derivatives. That's
Exactly.
like that's why it's like it clicked to me like how is this happening?
Yeah. No, the thing is, it's like basically you have the normal network and you just put this extra part to it to get the
Hmm.
output of the network to check if it's right. It's
Yeah.
think of it like having two networks which kind of checks each other's outputs.
Hmm. Yeah.
I kind of think it that way. And also there is another system where they talk about, they don't have it here. If you go into another network, when you talk about this thing, this Hamiltonian system of Monte Carlo methods, they have these two types of networks which treats. So when you take Hamiltonians in quantum
So
mechanics,
Hamiltonian just means like the second derivative, right?
uh,
Am I right? Or
in this case, they are talking about quantum mechanics.
okay, so I think maybe I'm
Like,
wrong.
yeah,
Yeah.
in this case, sorry, in this case, they're just talking about something in quantum mechanics where they have like imaginary numbers and like real numbers. And when you take
Hmm.
the differentiation, there is like imaginary component in it as well. So they create like two neural networks for each of these things, and they do it separately. So in a way, they have this ability to treat imaginary. They have a huge math behind it. They kind of
Hmm.
treat it as two neural networks, but they're doing the same equation in two
Hmm.
domains, and then they just like take a sum of it. Yeah, I still didn't get that part, so I probably need to do a bit on that.
But this was a great overview, dude. It was,
But yeah, anyways,
Yeah.
yeah. Thanks. Hope you guys enjoyed it.
yeah.
Very
Thank you
nice
so much.
presentation, Dilanjan.
No worries.
Thank you.
Awesome presentation. Thank you.
No worries.